science setters, welcome to today's grade 11 physical sciences show. Today we have a special revision lesson on gas laws and mole calculations. We have selected highlights from lessons shown early in the term to help you revise and prepare for your June exams. You can download the notes for today's show from learnextra.co.za/live. Now it's time to get on with today's lesson. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision.
Before we get there, we've got a question here which is based on Boyles Law, like I've explained, and let's just take a look at it and see if we can use what we know now, what we understand now, if we can come up with a way of solving this problem here. Now, it says here, a fixed amount of helium gas. Okay, so we're talking about a gas here. It is fixed. It has got a volume of 180 cubic centimeters. So we can write on the side here what is given to us. So volume 1 is 180. That 80 of mine, 180. Okay. 180 cubic centimeters. All right? And the temperature of the gas is at 30 degrees Celsius, and that is kept constant. The pressure of the gas is then adjusted, so it has been changed because the gas had to be checked on how it's going to behave when we change the pressure here. So it is changed from an initial value of 100 kilopascals. So our first pressure there was 100 kilopascals. Okay? And then this is adjusted to a value of what we have here. Okay, of 80 kilopascals. So we've got our pressure 2, or the second pressure, to be 80 kilopascals. Okay, so that is 80 kilopascals. Don't have space to write that there. Now, you're still keeping temperature constant because you are checking the relationship between volume and pressure. Here, we are asked to find out what will be the volume that the gas will occupy after these adjustments have been made. So the volume, the next volume of the gas will be something we don't know there. So there is the kilopascal. Right, now, from Boyles Law, what we need to know is that when we did Boyles Law, or we looked at the law, we saw that pressure is inversely proportional to volume. Now, if we put a constant here, or multiply by a constant k, so that we can remove this proportionality sign, what we will end up with is P equals K over V. So we have removed the proportionality sign by introducing the constant K. Now, this would mean that P times V would be equal to K, which is a constant. Okay? It will be equal to K, which is a constant. So this means that whether when you look at one point, maybe we can go back to this graph here. If I come back here and I look at this point, all right, let me just use a different color so we can see these points here. If I look at that point, there is a P value here. I will call it P1. And there is also a V value here, which will be V1. But I want to write this differently, and I will tell you why. Because you know when you write coordinates, you start with the horizontal one and then end up with the vertical one. So you've got the first volume of your volume here, of your gas here, which will be V1 there. And you will also, likewise, have your P1. So the coordinates that I have is V1 and P1 there. Now, when I choose another point, like this one, I will again have a p-value, which will be at point 2, and a v-value, which will be at point 2. So this will be v2, p2. Now, from what we have just come up with there in our, when we looked at the proportionality relationship and worked out the equation introducing the constant k, that would mean that if at this point here, when I have got P1 times V1 equaling K, even here, P2 times V2 would be equal to K, and because K is the same on both points, okay, we can therefore say here, at this point here, that the pressure at the first point times the volume at the first point will be equal to pressure at the second point times the volume at the second point. And from this, we'll be able to solve this problem here, where we are told those values there. All right, now let's put in these values here. Perhaps let me just do this. Okay, so these values here, we can take them and plug them in here. Now, how do we do that? What is P1? So let me use the space here. What is P1? P1 is 100 kilopascals. So for P1, I am going to write 100 kilopascals times. What was the V1? V1 was 180. These will be equal to P2, okay? P2 is 80 times. What is V2? V2 is what we are looking for. Therefore, V2 will be equal to 100 times 180 divided by 80, okay? And therefore, from there, we will be able to get what the second volume is, okay? At this point, we can bring the calculator and actually work it out. It's 100 times 180 divided by 80, right? And what is the answer? 225, okay? So it is 225 what? 225 cubic decimeters. Is it decimeters or centimeters? Let's just check what was given to us. We were given this in cubic centimeters. So this will be cubic centimeters, right? So we've been able to calculate for the volume there, making use of Boyles Law. If you like, this is the application of Boyles Law, all right? Now moving on, let's look at another law here. We call this one Charles' Law, okay? Charles' Law looks at the relationship between temperature, and volume, okay? Now, like I said earlier on, we are looking at the relationship between temperature and volume. Which quantity must be kept constant? Okay. It would mean that you need to keep the pressure constant and what? Pressure constant and number of moles of that gas must be kept constant. Okay. Now, let's read the law quickly here. The law says the absolute temperature is directly proportional to the volume of a gas, a fixed amount of a gas, provided that the pressure and, provided that the pressure of the gas remains constant. So you've got pressure and number of moles constant. So you can check the relationship between volume and temperature. Now let's see what Charles found out in this practical investigation. Now Charles found out that at a temperature of 0 degrees Celsius, already a gas is occupying some volume. Now the big question was, can we get a situation where a gas occupies no volume? And remember, go back to what John was talking to you about last week in terms of the ideal gases. Can we get to a point where this gas occupies no volume? And when he looks at this, he says, okay, this would mean if I have a situation where at 0 degrees Celsius, there is some volume already occupied by a gas. At what temperature will this gas, which would obviously be ideal, be occupying no volume? Okay? Then he looked at that and said, okay, if I have a scale, I need to take this one back now. Okay? If I have a scale where this part here, can be extrapolated, okay? Can it get to a point somewhere along the line where the temperature will be such that this gas occupies no volume, okay? And he did that. And actually what he found out was that these line that he came up with ended up at some point, right? So at some point, that point there. And at that point, he realized that this temperature scale works out to minus 273 degrees Celsius. And he called this the absolute zero. Now, this became the absolute zero. A temperature level at which the gas or a gas occupies no volume. All right. Now, when he has come up with this, he realized that if he can move this axis to this point here, he comes up with a new temperature scale where the absolute zero is at minus 273 degrees Celsius. And he calls that the absolute zero. Now, if that is zero here, it means at 0 degrees Celsius, it is 273. Now, at that point, what do you have? He says then, this is 0, that is 273, and therefore, he came up with this new temperature scale called, or he came to prove that we need a new way of measuring temperature, and he came up with the Kelvin scale, where to convert from degrees Celsius to Kelvin, you need to add 273. Okay, so you can see from here how that particular scale came about. Absolute zero plus how you get that gas to occupy no volume. The average global temperature from 1959 to 1999 is 14 degrees Celsius. And scientists are predicting that a rising in the average global temperature of 1.4 degrees Celsius by 2015 can happen. Now, the average lung capacity of a healthy young man, it's 6 liters. Now, liters are the same as cubic decimeters, so you can say this is 6 cubic decimeters. What volume will the lungs need to expand to in 2050 compared to today if the man wants to inhale the same mass of gas? This is an interesting question. And because it talks temperature, it talks volume, where can we locate it within the laws of gases? We locate it within Charles's law. That is where the relationship between volume and temperature is shown. So we can say from Charles's law that volume 1 over temperature 1 would be equal to volume 2 over temperature 2. All right? Now, what is volume 1? Or we can look at what is given to us in the question here. V1 is our 6 cubic decimeters, or 6 liters. It's the same. And T1, we are told it was 14 degrees Celsius, and we work in Kelvin. So with temperature, you always have to work in Kelvin, okay? You may not convert from cubic centimeters to cubic decimeters because you're going to keep everything constant left to right. But with temperature, you make sure you convert from degrees Celsius to Kelvin. So 14 degrees Celsius into Kelvin would mean that you need to add. You will need to add 273 here. And therefore, volume 2 is what we're looking for. T2 is given to us. We are told that the temperature will increase by 1.4 by 2015. So it means it will be 14 plus 1.4, which is 15.4. Okay, so that will be 15.4 plus 273. Okay, Kelvin. All right, so this is Kelvin, and that is Kelvin. Now let's try and work it out. Let's see if man is going to survive in 2015, and how much would a man need to survive in terms of the lung capacity. Volume 1, it's 6 over temperature 1, 273, or it's 14 plus 273, which is 28, that is 287, okay? That should be equal to volume 2 is what we're looking for, and this will be divided by 15.4 plus 273 will give us 288.4. Okay, so that's 288.4. Therefore, V2 is going to be 6 over 287 times 288.4. Let's make use of a calculator and see how much the lungs would have to increase by to be able to accommodate that particular situation there. So this would be 6 times 288.4 divided by 287, right? And therefore, that is 6.03, okay? So this will be equal to 6.03, and this is what? Cubic decimeters. Now, this is huge. Now, we're talking about issues of adaptability here because the environment is changing, okay? Species have to adapt to how the environment is like. Because we can't change the environment, we can only adapt to the environment. Therefore, by 2050, the capacity of the lungs have to increase by about, because it was 6.6 liters at first, or 66 cubic centimeters, the capacity of the lungs have to increase by 0.03 cubic centimeters. That is how much the lungs need to expand by 2050. Are we going to be able to do that? Is it going to be possible? And one way of doing it is to breathe quite faster, and you breathe quite faster, you're creating other problems. The heart has to beat faster. Stress on your body is going to increase. We're
Sure.
creating problems. The
Yes.
best thing is to take care of our environment.
That's it.
And that's the way to go. I mean, as scientists, we are saying whatever it is, however small it is that you need to do to contribute to saving the environment, please do it. Even if it means parking your car at home so that we can lessen carbon emissions, do it. Get into lift clubs, and
That's it,
we're doing our part.
We only have one Earth after all.
There can't be more.
Yeah.
There's no life elsewhere. It's only
No,
on
it's
planet
only on
Earth. That's what we have. So this is just to show us that we can't go after Earth. We may not survive.
Yeah.
Okay, we can't. We may not. We definitely do not have to choose after Earth. All right. So let's just have a look at it. Here is another question here that can actually help us again to try and understand these things here. The main cause of global warming is the increase in the amount of greenhouse gases, that is, gases like carbon dioxide, all right, in our atmosphere. A sample of 2.5 cubic decimeters of carbon dioxide at a pressure of 100 kilopascals is produced on the surface of the Earth. What volume will this gas occupy at 45 kilometers above the Earth, where the temperature is assumed to be the same as on the surface of the Earth, but the pressure is 5 pascals? Now you see in this situation you've got pascals, you've got kilopascals. You can't have kilopascals on one side and pascals on the other. You have to work on one specific unit. Now let's just write down what is given to us. P1 is 100 kilopascals, okay? 100 kilopascals. And then V1 is 2.5 cubic decimeters, all right? And then 45 kilometers above the surface of the 45 kilometers into the atmosphere, we've got a pressure of 5 pascals. 5 pascals, and therefore we need to know how much volume can be occupied by this. Work together with me. May not have all the time to finish off this problem, so you can finish it on your own, but let's have a look at it. You can use Boyles Law, obviously. So P1, V1 equals P2, V2. But remember, you have got pascals and kilopascals, all right? You've got pascals and kilopascals. Now, kilopascals can work together with pascals. We need to convert that, all right? So 100 kilopascals in pascals, you multiply this by 1,000, is going to be 1 by 10 to the power 5 pascals. All right, so you would say, okay, for P1, it's 1 by 10 to the power 5 pascals times V1, which is 2.5. That will be equal to P2, which is 5 pascals, times V2 that we don't know. Now, what will V2 be? V2 will be equal to 1 by 10 to the power 5 pascals times 2.5 divided by 5. Okay? And what will this work out to be? Quickly, we've got 1 by 10 to the 5, 1 by 10 to the power 5 times 2.5 divided by 5. And what is the answer? This works out to 50,000. So 50,000 cubic decimeters. Now, a gas that occupies so small a space on Earth occupies a huge space up there. That's what it means.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. We have got such exciting news for you. From July, a new program starts on Mindset, just for you. It's called Connections. We'll chat about the issues that affect your life, your school, and your relationships. We'll have fun, take your calls, and have great prizes up for grabs. Connections, from the 1st of July, 7:30 in the evening, only on Mindset. For you, by you. Welcome back from the break. I know you can't wait for the term to end and the July holidays to start. And of course, that means winter school. This year, we will be repeating all the Term 2 Learn Extra live shows for you from the 24th till the 28th of June from 9 a.m. in the morning till 7 p.m. at night. So don't miss out. Go to our website www.mindset.co.za/learn/extra/winter school to get all the details and to download the notes for each lesson. But for now, let's get back to today's revision lesson. Over to you.
Question 1. Okay. A certain mass of carbon dioxide gas is sealed in a 0.2 cubic meter container. The gas exerts a pressure of 100 kilopascals on the sides of the container at a temperature of 25 degrees Celsius. Calculate A, all right, so we've got A here. Calculate the number of carbon dioxide gas moles present in that container. How do we do that? Now let's just write down all the things that are given to us. Let me just go back there so I can see them. All right. We have a volume of 0.2 cubic decimeters. So V is 0.2 cubic meters, actually, not cubic decimeters. And then we are given a pressure of 100 kilopascals, right? And we also have the temperature of 25 degrees Celsius. Now, we want to know the number of moles. N is what we need to know. Now, if you look at these three things here, V, volume, pressure, temperature, number of moles, the equation that puts them together is actually the universal ideal gas law, which says PV is equal to nRT. We will be able to find what N is if we use that. But then here, the challenge that we also have is the fact that some of the units here are not given to us in the required SI units. We said that with pressure, you need to make sure that you have it in pascals. And what is 100 kilopascals in pascals? You need to multiply this 100 by what? By 1,000 to go into pascals. So 10 to the power 3 pascals. Another thing, with volume, we don't have to change anything. It is in cubic meters, we find. With temperature, we don't work in degrees Celsius, we work in Kelvin. So it will be 25 plus 273, so that we will have this in Kelvin. So this works out to 298, okay? So that is 298 Kelvin, 298 K. That's what it works out to. Now, with all this, we will be able then to solve this problem here. Now, when you are to solve problems in science, those that involve calculations, first thing you do is to write the equation or the formula. Now, let me rewrite it because I want you to always do it the way I do. Now, P is what? When you come to this point here, once you have written down your formula, what you need to do is to substitute into it. Don't try and make what you are looking for the subject of the formula. In this case, you're looking for number of moles N. Don't try and look for the N or trying to make N the subject of the formula, because we know that sometimes, not always of course, sometimes you make mistakes when you are changing the subject of the formula. So we want to spare you that problem, and you still gain marks in doing what you're going to do now. Just watch what I'm going to do. What I'm going to do is to substitute what I'm given into this equation here. What is P? My pressure is the pressure that I have, or given to me here, is 10 or 100 times 10 to the power 3. So 100 times 10 to the power 3 pascals. Okay? The volume is 0.2 meters, equal. N is what I'm looking for, all right? Now, times R. What is R? 8.31. Times T. What is T? We found T to be 298. I hope I'll have space for it here. 29, I won't have space. Let me just have it down here. So this will be equal to N times this will be equal to N is what I'm looking for, times 8.31 times 298. Okay? So 298 is my Kelvin temperature. From here, I can then just use my calculator. Let's just have a look at the calculator. I've got 100 by 10 to the power 3 times 0.2. So I've got this. 100 by 10 to the power 3 times 0.2. Okay, 0.2. What I have here now is 20,000. So I've got 20,000 here equal, what is 8.31 times 298? Let's just work it out as well. So 8.31 times 298. 298. What will that be? That's 2476.38. 2476.38 N. Therefore, my N is equal to this 20,000 divided by 2476.38. So it's 20,000 divided by 2476.38. What do I have? I have the number of moles being 8.07. Oh, 07 moles. Okay, so I can have the number of moles like that. Okay, and if I have the number of moles, I come to question number B here. The question number B wants me to get the mass, okay? It wants me to get the mass. Now, this is a huge number of moles here for me to get the mass there, but I will be able to get it. The only thing is that realistically, perhaps that wouldn't have been the number of moles that are kept in that particular container. But this is for our exercise. Let's just have a look at how to get the mass there. Remember, for number B, you are to get the mass of carbon dioxide gas inside that container. How do we do it? From here, we will need to go and say, all right, number of moles is also given as the mass of a quantity divided by the molar mass. Remember, capital letter M means molar mass. Now we're talking about carbon dioxide. It means here we will need to find out what is the molar mass of carbon dioxide. And how do we work that out? The molar mass of carbon dioxide, M, would be found by going to the periodic table and you look for the molar mass of carbon, the molar mass of oxygen, put them together, they give you the molar mass of carbon dioxide. So let's have a look at carbon. If you checking your periodic table, you'll see it is 12 plus for oxygen, it's 16. So it's 2 of the oxygen atoms there. So it's 2 into 16. So we've got 12 plus 32. And that gives us 44 grams per mole. Okay? 44 grams per mole. Right? So that is what we have here. 44 grams per mole. That is the molar mass of carbon. So if I want to get the mass, because that is what question number B is asking me to do, it means I will substitute what I have now into this formula. Number of moles is 8.07 equals. The mass is what? Mass is what we are looking for from that question there. The molar mass is 4 grams per mole. Therefore, the mass is going to be 8.07 times 44. It's going to be a huge mass, but this is about us learning how to do it for now. So that will be times what? 44. And therefore, it's 355.35 grams. 355.35 grams. Okay, so that is the mass, 355.35 grams of the oxygen gas there. So that is how you can use these formulas. You move from one thing to the next. The idea here is to say you must not forget that N equals M over M still apply here because we're talking about number of moles. Although we can get the number of moles from what we know in gases using this other formula here, that number of moles will be the given gas divided by the molar volume. Given volume of the gas divided by the molar volume when we're talking about standard conditions of temperature and pressure. But then from this, also understand that the same N is the same N that we're talking about here. So you can use these equations here to interchangeably to solve your problems, as long as you understand where you are coming from.
Now it's time for a break, so don't go away. We'll be right back. Welcome back, Mindsetters. In case you missed my news, starting in July, we have a new program that is going to get you talking. What's on your mind? What are the issues you deal with? How can we help you? Connections will help you with all that and more, so make sure you catch it. For a fun and youthful look at life, connect with us on Connections. But right now, let's do some more revision.
There we are, question 1. What is the volume of 3 moles of nitrogen gas at STP? Now, there are multiple ways you could answer this. You could, if you're very happy with ideal gases, go and throw this into PV is equal to nRT. You've got the temperature and pressure on your data sheet because that's the standard temperature and pressure. But we could also work with this equation that I have just worked with you. We've got the number of moles, we've got the molar volume, and that was 22.4 dm cubed. Okay, more moles per dm cubed. Let's just take that out and write in here moles dot dm to the minus 3. So I have N is equal to V over molar volume, and we have got the number of moles and the molar volume. So let's try and find the volume. What are we going to do? It's dividing that side, so it comes across and multiplying. Vm is equal to V. Number of moles was 3 times by 22.4, and we get to, well, let's just throw that into the calculator. 3 multiplied by 22.4 is equal to 67.2. So I come across here, my answer 67.2 decimeters cubed. Now that is the volume of N2 at standard temperature and pressure. And grade 11s, I want to really highly recommend to you that what you would do with these is that you would make sure that when you write your final answer to a question, finish it off by saying what we're working with. Okay? The reason I suggest that to you is because we're now going to start to work with long chemical equations, and we might be working out the number of moles of one substance and another substance in the same question. So do that, and it will help guide you in terms of going back and checking that you've got the right substance in terms of answering your question, and you won't confuse yourself. So I think we should head for a break soon. And what we need to do is we're going to come back, we're going to look at concentration, and then we're going to tackle plenty of questions. So here we're looking at making up solutions, and so I want us to practice that right now. I want us to note that we are looking at making up a solution of sodium hydroxide. Sodium hydroxide's formula NaOH. Okay? 17 grams of that, sorry, we should have the grams there. 17 grams of sodium hydroxide is dissolved in water, and the solution made up to 250 cubic centimeters. That is my volume, all right? This 17 grams is the mass of the sodium hydroxide. And they asked me to calculate the concentration. So let's head down to the bottom where I can have some space, and I'm going to write down those values. We've got concentration is the question. That's what we're trying to find. My mass was for 17 grams of sodium hydroxide. What else did I have? The volume was 250 centimeters cubed. Now, firstly, we have to get into number of moles, because as you'll remember, this is my equation, number of moles over volume. I don't have number of moles. So firstly, we need to take whatever our value is here and go from a mass down to a number of moles. Okay? Then from the moles, I can work that into a concentration. Okay? So firstly, we've got to go from mass to moles. How do I do that? Well, I've got the mass of my sample, and I need another value. I need the molar mass. So on the side here, I'm writing molar mass of NaOH. Okay? That is the sodium hydroxide. We go across to the periodic table, and we need to go and find those. So sodium, there it is, with, let's change the color, 23. Oxygen, we had it earlier, 16, and hydrogen, 1. Remember I said use the periodic table that you've been given, because you might have decimal places and things like that. This one's been rounded off. So here we're coming back, and we're going to write, what was it? 23 plus, oxygen was 16 plus, hydrogen was 1. And we can work that out. So our calculator, 23 plus 16 plus 1 is giving me a lovely round number of 40 grams in 1 mole. Okay. Now I've used the slash there, or you could write it as 40 grams dot mole to the power of minus 1. So let's take that mass and work it to number of moles. I'm coming across here. Number of moles is equal to mass over molar mass. And I had 17 divided by 40. Okay? And that's going to give me the number of moles of sodium hydroxide that I'm including into this solution. So let's go across to the calculator. And we have 17 divided by 40 grams in 1 mole. And that's 0.425 let's jot that down, 0.425 moles of NaOH. Okay? The focus here, you might say, but I know it's NaOH. The trouble is that you might have many sub-questions to this big question. And I highly recommend that you just jot that down so that you know what you're working with. You can come back to it and work with it a lot. Okay, so that's the first part of the question. Have we answered the question though? Check. The question asked us to find the concentration. We haven't done that yet. We now have the number of moles and we have the volume. So we can go and use our final equation and plug that in. The thought, before we move on though, is my volume in the correct units? Okay, we got told it was 250 cubic centimeters, but concentration is worked out in cubic decimeters. Okay, moles per cubic decimeter. So I first need to go and convert this, and I'm listing it over here. Well, cubic centimeters to cubic decimeters, I must divide by 1,000. So 0.250 decimeters cubed. Okay, because there are 1,000 cubic centimeters in a cubic decimeter, so I need to divide by 1,000 to go from cubic centimeters to cubic decimeters. And so I can work on my final equation. Let's go. Concentration is equal to number of moles over volume. The number of moles, I worked that out. 0.425 moles. And that's divided by the volume. Watch out, we had to convert that volume. And the volume was 0.250 decimeters cubed. And we can get to our final answer divided by 0.250. And we get 1.7 moles per decimeter cubed. Okay. Now, just a thought here. You might have rounded off your answer at this point, and that's absolutely fine. So we could have rounded off to 0.43 to 2 decimal places moles. That's absolutely fine. And if we had done that, going across to my calculator, let's just 0.43 divided by 0.25, and you're going to get a very similar answer. Okay, what was it? 1.72 moles per decimeter cubed. Okay, very helpful to always write down your answer and work with that.
Now it's time for a break, so don't go away. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you on the page or on Twitter. Enough of the chat. Let's get back to revision.
Let's have a look at it. Given the following reaction, and here we are, 3NO2 plus water forms 2HNO3 plus nitrogen monoxide NO. First thing I want to notice before we go any further is to notice these are all gases. They're all in the gas phase, right? How do we tell that? Well, we get given those little small g's, which means this is all in the gaseous phase. Next, if 2.7 cubic decimeters, dm cubed, of NO2 is used, what volume of HNO3 is produced? Okay, so I want us to just go through what we've got, and I'm going to take off these little circles because I've noted that they're all gases, and what that's going to tell me is that I can work firstly with the number of moles is equal to volume over the molar volume. So we get given a volume here for nitrogen dioxide. So immediately I'm going to actually rewrite this equation, because I'm certain that when you start on your piece of paper, you're going to want to have the equation written at the top of your page. Okay, there's our reaction, our equation, HNO3 plus NO. You've got that spaced across your whole page. Now we need to look at what we're being asked to do. We've got a volume here. V is equal to 2.7 decimeters cubed. Okay? I'm putting that information directly underneath nitrogen dioxide, and my question is, what volume of HNO3? So next, underneath this one, I'm putting volume equals question mark, because that's what I'm going to want to find. Now, what did we say about the mole calculations? Mole roots convert to number of moles, and then we can compare. So let's do that first. Let's go across here. Number of moles is equal to volume divided by the molar volume. Let's give ourselves some space to write. What volume did we have? We had 2.7 decimeters cubed, and we are dividing here by 22.4 decimeters cubed. Why is that? Well, it's because for 1 mole of gas at standard temperature and pressure, the volume is going to occupy 22.4 cubic decimeters of space. So it's a helpful number to have. It's on your data sheet. You would go and work with that molar volume, and we're going to get an answer. Now let's find our calculator and work it out. It was 2.7 divided by 22.4, giving me my answer. Let's have it as a decimal, 0.12. So going across here, 0.12, and it's going to be moles of NO2, all right, because that's what I was working with. Now, I need to get from NO2 all the way across to HNO3. So how I'm going to do that? I'm going to compare with the mole ratio, right? So let's take this down and work with my mole ratio. What does the balanced equation say? The balanced equation says it is a 3:2 ratio. So I'm going to write that down. It is a 3:2 ratio, which means it's going to be 0.12 moles is to, how am I going to work that out? Well, firstly, I need to divide by 3, and then if I want to move across to that side, multiply by 2. So, going back to my calculator, 0.12 divide by 3, multiply by 2, and that's going to give me an answer, 0.08. So, is to 0.08, and the unit here is moles, but now what? Moles. Moles of what? Moles of HNO3. Go back. That was what I'm working with. So the big jump from the one substance to the other substance, the only way I can compare them, the only way I've got information about both of them, is the ratio, the mole ratio that we're working with, right? So I've got the mole ratio here, and this is of HNO3. Now, I can work out what I'm asked to work out, which was, what is the volume, I believe? Let's go back and check the question. What volume of that is produced? It was also a gas, so I can still work with that same equation. Number of moles is equal to volume divided by molar volume. Let's rearrange it. Volume would be equal to number of moles multiplied by the molar volume. And I'm just writing that, showing that we're taking across from a denominator, it was dividing, take it across the other side, it's now multiplying. So 0.08 multiplied by And what is the molar volume? It is 22,4 cubic decimeters. So 22.4 would be equal to the volume. So volume's answer, let's go and work that out. It's going to be multiplied by 22.4 equals 1,792. So going back here, 1,792, and let's round that off, 1.79 decimeters cubed of HNO3. Okay, that's the final answer in terms of what is produced. Let's go back and work through exactly how we worked that out. We first observed the balanced chemical equation. Then what we did was we converted whatever information we were given to number of moles. So we had a number of moles that we could compare via the mole ratio. So I'm going to just, in a separate color over here, write up our plan of action. Volume, I converted to moles. Once you've got moles, you can compare and get the moles of the second substance, the other substance. And then we had to answer the question, and we took that back to a volume. It's quite helpful just to have a plan of action in mind in terms of how you're going to work this through. And when we're going to come back for this from this next break, we're going to look at limiting reagents and comparing some more of these types of questions. But it's so vitally important that you always follow through all of these types of questions and think through what you're doing. Convert to moles, compare the mole ratio, and then work out your final answer.
We've come to the end of today's show. Thanks to Macmillan for making the show possible, and thank you for joining me and for participating in this revision session. Remember to join us for winter school from the 24th till the 27th of June, when we will be repeating all the Learn Extra live shows from Term 2. We will be back with live shows from the 15th of July for Term 3 lessons.